right. Welcome back. Um, so, welcome back to the Friday Open Studio design session live stream that I'm doing every week. So I guess just a quick update on where we left off before we dive into it. Right now we are trying to create a kind of a model of F-16. As you can see, this is how far we've gotten so far. And these are some of the parts involved. Kind of the goal with this is, hello, Boats Border. How are you doing? I'm just reading some chats in the live chat feature. Hopefully this week goes a little bit more smoothly. We won't have any technical difficulties, but you know, in case it does happen, I'll have to delete the stream again and then start another one. So hopefully that doesn't happen today. Just you know, right now I just want to kind of update you guys on where I am before I lost my train of thought there with the with the live chat. So yeah, we're creating a model F-16. Yeah, and really the goal here is to make a return to, I guess, normal, like real life aircraft. You know, the past several projects that I've done involved doing, I guess, you know, I did do a real life aircraft. It's just a little more futuristic. This is taking it back a notch. You know, this plane was, in real life, it was designed in the 70s and 80s. So, you know, we're going back and doing some old, relatively old speaking, 50-year-old design almost. Just a real life design. But anyways, you know, so instead of like, you know, doing just a simple F-16, in this project we are aiming to implement some new, I guess, designs for mechanisms. And you know, the reason I do mechanisms is not because, you know, it's, I guess, too functional per se, because, you know, you don't really need it to be able to fly. But, you know, a huge part of what I do is kind of revolved around appreciating the things that enable us to be able to fly, right? So airplanes, you know, to me, mechanisms are a way of giving these models a little bit more heart and soul, I guess. It's kind of a abstract thing to, you know, say. It doesn't provide like a concrete benefit. You know, like I say that, but you know, on the scale, it's not that much, right? So if we're talking like leading edge slats, for example, we're in the process of making this mechanism. It is not very, you know, at the scale, you only really have like approximately a centimeter or so of, you know, surface that, you know, when you're at a high angle of attack, you want the air to flow over. So, you know, at this low of a Reynolds number, you know, which is, you know, there's an equation for that, which basically it describes aerodynamic scale, right? So at this scale, at this really small, you know, about the size of my hand kind of scale, air behaves differently than, say, on a real life F-16. So, you know, these features don't really make sense with regard to, you know, hardcore performance. But, you know, to me, right, like I said before, mechanisms, you know, movement in the actual model, right, connected features, right, that you can, you know, you have a central rod here that we're going to install eventually, and having like these slider points, right, like you have a knob that you can slide back and forth that actuates this mechanism, that gives it a little bit more, you know, kind of appeal to it, right? Things that move kind of interest people, right? You see those other videos on YouTube with, like, you know, the marble machines and, you know, just mechanisms in general, right? They get a lot of views because people are curious, how does it work, right? So it's really interesting to see things move, and that's why I'm incorporating some of these mechanisms. Um, so in the last stream, which was last week, we left off at a point, I think, where we determined. So we made the actuation links, as you can see here in the orange paperclip, steel wire basically. Um, and I'm trying not to move this, shift it too much, but as you can see, this mechanism lines up right here. We finished cutting the windows last time in the central, I guess, bearing, linear bearing. So you have like, so let me just pull out an example, right? You have two types of straws involved in this mechanism. You have this large diameter straw, courtesy of Dunkin' Donuts. When I get their iced coffees, I stock up on these straws. But also you have these thin diameter straws, which you probably see more in I don't know, like a kind of, I don't know, Starbucks environment, right? These are like simple black straws, and so two of these, when they're pinched down, right, when you like really compress it, two of these can fit inside one of these, right? And then that's what I call my friction lock module. It essentially exerts a lot of normal force outwards and creates a ton of friction between this double, kind of double, I guess, thin diameter straw inside this, right? It's just really tight in terms of friction, and that actually works to our advantage here, because the coefficient of friction is actually just slightly enough to keep it in place, right? This is plastic on plastic, if you think about it, right? With a lot of force, it kind of sticks, right? It's kind of hard to describe, but if you try and rub straws together on the inside like this, right, it kind of sticks, and then you can move, but it likes to stick in a certain position, and this essentially enables us to create a mechanism that doesn't shift, right? This is a stable way to move things linearly, and so that was, I first designed that kind of configuration or mechanism years ago, but we're still using it now because at this scale, when you're using office supplies and just things around the house, this actually works really, really well. So last week we ended up cutting a little window here, and we explained that this was to simplify the mechanism. Instead of having like an open end with a moving piece going back and forth, we can have everything be encapsulated inside this orange straw and have a slider pin move back and forth instead of a whole section of straw move back and forth. So these, I went over how to make this, right? It's just a matter of craftsmanship at this point because it's really hard, right? It's a very thin feature. Essentially you have to make your fingers into a jig and then do a straight line like that and keep it steady, right? And then the same thing goes for cutting, right? You have to cut one side first and then the other side that's parallel to it, and then you want to cut this end point here, and then you can fold this tab of rectangular plastic over, and then you can slice it off. And so that's just kind of some of the manufacturing techniques that we went over last week. So we made that for the tail section here, which is the horizontal stabilizer. Essentially, this isn't folded yet. When this piece is done, it'll be the tail. Imagine like a diagonal line here. That's the leading edge, right? If you fold it over, that's gonna be the leading edge. So yeah, that's kind of where we left off. We made that, and we also spent a lot of time last week trying to bend this actuation link into shape. And this actually, if you if you listened in last week, this took a lot of effort. This is not easy to make, but once it's made, it's like a very reliable part, right? Because it's made out of steel, it's going to retain its shape pretty well. Um, and this is absolutely necessary for the leading edge slats, which we want to incorporate in this design. Again, I might not have mentioned this in this stream, but the whole reason behind this, dual mechanism linked by a common input is the idea that when you deploy your leading edge slats down, you also deploy your horizontal tails down, right? And that pitches your plane up, which makes sense because when you're pitching up, you don't want the air to separate over your wings, right? Your wings turn up like this, and then the air is going to separate, but you don't want that to happen. So you want the leading edge slats to point down, right? Which helps guide the air over. And so with this configuration, we're able to do that, right? We aren't able to do that in several other configurations. The main one being the wing in the back and the canard in the front. You're not able to synchronize that movement because they want to go in opposite directions in order to pitch the plane up, at least for lifting canard. I didn't get into all the detail there, but the gist is that this configuration on the F-16 is a perfect place to incorporate a a mechanism that connects two moving pieces. I guess it's really four, actually, four moving pieces, but this tail section here I plan on making out of one continuous piece of wire so that we don't have to separate it into two parts. But that's in the works. So last time, at the end of last week's stream, we discussed how to proceed forward with this mechanism design. I know it was kind of fuzzy. It's kind of fuzzy in my mind now because it's been a week, but I think the idea was to start in the back and work our way to the front because we want to actually, constrain as much of this mechanism as possible before we can start, implementing, the rest of it. What I mean is because this mechanism is so tightly integrated, right? You have this moving part and this moving part. I think it's just easier if you start at one end and work to the other. And the reason why we can't do that for the front is that we need a little bit more work here, right? So we essentially have to I'll explain this bearing. I tried explaining this in the last stream, but I'm not sure if any of you got it. It's actually fairly clever. It's simple, but it's hard to wrap your mind around. This is going to be acting as a bearing here, right? We're going to have this be able to turn, but then, essentially we're going to have to connect. I'm going to have to connect the orange to the spar, right? This is a popsicle stick wooden spar. I have to connect the orange to the spar first, and then once that's done, then we can apply this, the front actual surface, which is the leading edge slat, onto this orange wire piece. And that's a very tight integration, and I guess we could do it that way. We could actually work our way from the front to the back, but I think before I do that, I want to have a better feeling of what it's gonna be like, this mechanism. So to do that, if we make the tail and kind of constrain it in a way, right? Because this actuation arm, right, this link is gonna be right here, moving back and forth, right? You have a pin that's gonna be sliding in the slot, and then you want to be able to adjust that as you place the slats in place. So essentially we're going to be trying to constrain one side before we proceed with the next. So I guess, kind of Right. So the idea, I think, the idea here was to, so essentially this, I guess these moving parts can be done, but since this one is more critical to the internal moving straw, this one is more critical. That's why we wanted to start with the back here, because if we do that, then we can fix this neutral position of the pin in place. And then once this neutral position is in place, then we can puncture this and then define where this part interacts, right? So that's kind of the thought process behind that. That's why we want to go with the back side first. So I'm just kind of like thinking out loud to myself. So again, this is an open studio design session. So if you have your own projects, I encourage you to work on them as well, right? In the meantime, just kind of listen in on this, have like a working studio environment to work on your projects. So yeah, let's get started here. We really want to make this empennage mechanism right here first. That's gonna be interesting. Let's just zoom in a little bit more so that we get a better look here. So this mechanism is going to be aligned here, right at this mark at the edge here. And you know, once it's in the center, you can really start messing with it. So we have the hinge line marked here. It's the hinge line for the horizontal stabilizer. And then this is where the leading edge ends. So it has to be aligned like this. So our part is gonna come into this piece right here and then come around like that. I don't know exactly how long of a link we're able to make, but we'll have to mark out the path along which we want the rod to go. So to do that, I think I'm going to mark out the diagonal where the leading edge is first, and then go from there. So let's just move this to the side, right? Just keep in mind we're working on this part, so I'll just keep some of it in frame, but we're gonna essentially take a ruler and line these 2 points, right? Let's see which one's inside, which one's out. I want this side to be on the inside because the edge is a little bit rough. So when it's folded in, it'll be smooth on the outside. So I'm gonna mark this, right? And then this. Just slide that across, right? So we have one done, and I'm gonna just do the same for the other side here. Just gonna mark the corner here, right? Align it with the tip there, and just slide this across. All right, that's pretty good. All right, so now you can get a feel for the actual part, what it's gonna look like in the end, right? You have this edge right here, which is nice, right? And you're gonna have another part right here. It's gonna be fitted here. I'm noticing it's a little bit off for some reason. Nah, it looks fine. It looks fine. It's I think it's a matter of how I drew the line on the fuselage. It's a little mismatched there, but right, it's not a very okay. I guess it's fairly close. It's lined up, so that's good. Need to figure out a way to mark where we want the wire to go. So for that, I think I want to just go in a little bit, as close as we can to this edge, but we don't want it to be too close because we need enough clearance for this thing to rotate, right? So let me just move this over a little bit so I can get a better angle here to look at. You need to set a slight distance, right? Offset. Because when you fold this over, you don't want the orange, the wire, to be right at the tip. Actually, I don't know if that's true. If it's right at the tip, it's gonna be hard to predict where the paper is gonna go. I think it's better to offset it a little bit. All right, let's call it I'm trying to decide what's a appropriate margin here. Like 1.5 millimeters to 2 millimeters. I'm gonna do 2 millimeters. Once that wire comes out and we make the part, this inner edge here has to be sealed, just for protection. And when we do that, we're gonna need a little bit of margin here to kind of allow that surface to meet, right? So if you imagine our tail, we'll do a quick sketch here on a sheet of white paper. We have, our cockpit, right? And then your fuselage here, and then your wing, right? And then your tail. If you zoom into this tail right here on the F-16, it's angled down, right? So we'll capture that with the wire work, with the metal work. But we also want you have your cockpit, and I'm just trying to make it look a little bit more realistic here. You have your intake down here, right? Whatever, that's your F-16. So if we look at this tail section, if you look at the cross section, right, it's gonna be like a thin piece of cardstock. Or this is not the cross section, this is the front on view. Essentially this is going to have a metal wire on the inside connecting to the the fuselage. And on the real life aircraft, there's this very sharp edge, I guess. I did a design study, sketch of it in my notebook here. Let me just grab that real quick. So if you just look at the drawing here, right? So this is kind of what I'm talking about. So you have your tail, and this section right here is like a vertical edge. It's like a hard edge. I think the reason for that was that initially they intended this structure right here on the F-16 to be a support for kind of a vertical tail as well. So this serves two functions, right? This serves the horizontal tail anchor point, right? As well as the vertical tail. That was like the initial prototype of the F-16, I want to say. But they decided to go with a single, vertical tail, right? We end up with a F-16 with a single tail. And that caused this to just lose its function. And so it's not aerodynamic looking. It's just a straight edge going down. Like if you look from the side, it's like a block, right? Right. If you look here on this isometric sketch, it's like a straight flat edge vertically. But that's kind of a small detail that I noticed. But in our build, essentially we want to give this mechanism, right? So once our wire comes in here, we want it to have enough gap. So we have a tail shape, right? It's like this. Essentially, we want the wire to come in, go back like that, right? Maybe come in. I am not sure, because this really depends on how much length we have in a standard paperclip. So the length is questionable, but we want this edge right here to be taped, right? This edge needs to be secure, as well as this edge on either side of this actuation link, right? And then to do that, we can't have this wire be right on this edge where it ends. We need to have this wire offset inwards so that we can get kind of a shape like that. This is a head-on view, right? So if you imagine a leading edge there, right? You don't want it to be right there, because then you can't really complete it. If we have an offset, we can pinch this inner lip. That's kind of the idea I'm trying to express here, and that's why I went with the 2 millimeter measurement here, offset. So we need to draw a line here horizontally, parallel to the aircraft axis, right? 2 millimeters offset in. So I'm just gonna do that real quick right now. And this is really, it's very small. It's not a very obvious detail, but to do it right, I feel like maybe even 3. We might need 3, right? Because depending on the thickness of this metal wire, we might need 3 millimeters. I think to be safe, I'm just gonna do 3. That should give it enough space to pinch in and close off this tail surface from being open. So we want 3 mil, and then to draw a parallel line, we're just gonna mark 3 mil here, and then connect the dots. Okay. This is why geometry is so important in school. All right, so let's just line this up, right? We have, okay, you know what? We're gonna mark this one as the right side horizontal surface, horizontal tail. R for right side, all right, starboard, right? That black dot is misleading, right? I'm gonna try and erase that. All right, there we go. It's been erased. So if we line the leading edge up, the hinge line, which this is not like a precise thing, right? I think I just looked at pictures and then decided, okay, it's gonna be right here. And it looks about right. Like the hinge line is not, exactly in the middle, but you know, in the real life design, this thing is like an engine nozzle right here. So I'm assuming it's not going to be like too aft. So I just kind of determined like a hand wavy, like, okay, it's going to be right here. And so that's how we determined this hinge line right here. So with that, you know, we can mark where the hinge line is going to be, right? This is the hinge line coming in. I want to wrap this around here, and then, you know, maybe like a 2 millimeter offset from the actual leading edge, just to give that leading edge a sharpness to it. It is a fighter aircraft, so all the airfoil cross sections are, you know, super thin, right? They're super sharp, and to enable that kind of geometry, we don't want the wire to go all the way to the front. We want to offset it by 2 or 3 millimeters. In this case, I think let's just go with 3 to be safe, right? Keep it consistent with what we had for the hinge. And this is 3 horizontally. This is not, you know, perpendicular. 3 this way is different from 3 this way. So as more is important to keep in mind, right? So you don't want to do that. Although I guess to keep consistent, I should be doing it the perpendicular way, but this looks decent to me. Yeah, this looks right to me, so I'm just gonna keep with this. I don't know how much length we have, so I don't know exactly yet what the part is gonna look like. If you connect the dots here, you can get a general idea, right? So this isn't gonna be a sharp corner because we were not able to create that. It's gonna be kind of like a rounded point here for the actuation link. So if it does have enough length, I want it to kind of extend out a little bit. And then, okay, that's not exactly parallel. There we go. We fixed it. Just get rid of some of the thickness in this line. Really, that's all we need is this. Although I'm not sure, like, because this is kind of a triangle, right? The 3 points here, if you just have it like this on the inside, this edge right here is gonna, like, you know, this area might be susceptible to folding, right? If you strike the ground at a bad angle, this, you know, because these 2 points are rigid, and then there's no support material in the back here, so it's gonna be able to bend. So I think we might need to do like a little extension here. Again, I am not entirely sure how much length we have, so we could do like a family of horizontal lines extending off at different points, and then decide once we have the part in process being manufactured, decide what the appropriate amount is. So I'm just gonna eyeball this, all right? Just eyeball the parallelness here. So we can do it at the end. I'm thinking of breaking this into thirds. So this is about 3 centimeters. We could do one at 2, and you could do it. Okay, we're probably not gonna do the one at 1, because that's kind of dumb. That's way too short, not enough area. We could have it go diagonal, but I don't want like crease lines to show. So it's easier to hide crease lines if you go with, right? So I marked one at 2 centimeters. I'm not sure that's enough. Just kind of eyeballing where the potential wire could end up. Half is a little too little. I don't think that's enough. Also, it'll look bad if you have a crease line right down the middle. So 2 centimeters, which is 2/3 of the way up, and then 3 centimeters. That looks about good. Yeah, okay. We do need to mark the other side, right? So this side right here is gonna be the left side tail. So I'm just gonna mark that as an L, right? We're gonna try and duplicate what we did here, just to have a reference, right? It's always good to have a reference. So 3 millimeters off. Right? Oh shoot. Alright. Bad angle. 3 millimeters. And then okay, this is three non-collinear points to determine a plane. I'm just citing geometric facts at this point, but that's that. Right. Draw, we can match up the hinge line because ideally they're going to be at the same location. Right. Since it's such a short line, we're able to freehand this without much ado. And then 3 millimeters off the front. Okay, so I'm just going to take off some of these construction lines just to clarify things a little bit. Part matches up nicely. 3 mil horizontally off from the diagonal here. That's 4. That's 3. There we go. Okay. I want to do the same thing here. We want to be parallel to the aircraft axis, which means, and since the trailing edge is perpendicular, we can just do it like this. So it's 1, 2, 1, 2, 3, about right there. Okay. You don't always have to use 0 as a reference point. You can use other reference points on the ruler. You just have to make sure, keep in mind, right, what the starting point is. Make it easier on yourself to measure. Okay, essentially connect the dots at this point. It's pretty parallel, I would say. Let me fix it a little bit. Okay. And our options were, this one was, I think it was approximately 3. It's not exactly 3. This is like 2 and 2.75, 2.75 and 2. Okay, let's just call it 2.8. 2.8 and 2 off from the inner edge here. So 2.8 would be right about here, and then 2 would be right about here. I just need lines connecting there. Again, right angle. Just zoom in a little bit. Looks pretty parallel to the aircraft axis. This is not a flight critical piece, but it's always nice to have a well-made end product. Okay, at least, well-made to the best of my abilities, right? Can't be machine perfect. Even machines aren't perfect, so there's always going to be tolerance issues. It's just how tight you can control those tolerances. That's the key. Okay, I'm going to erase that construction line, right? I'm going to also erase this construction line to not confuse ourselves in the process. Okay, so we have the wire pattern laid down. Zoom out a little bit. There we go. Whew. Okay. The two horizontal tails marked out. This is where they're going to connect. Now we just need we need to have an idea of how thick we want the connection to be, or rather, I don't know what to call that part. It's kind of like a bridge connecting the two, so I'm just gonna call it a bridge. But essentially, you have your mechanism core, which is the circular cross section. You have a wire coming in, a wire going over, transitioning into curve, going over, right? And then coming back down on the other side. The question is, how wide do we want this? Right. What's the width? And what exactly is the height? And that's the question due to be answered here. Once we have that information, we can start to fold the wire, I guess. So we also need to know, in addition to that, the distance from this location, this corner right here, to the place where it starts to come out of the page, right? So if you took physics in college, the circle is coming out, X is going in, right? It's like if you imagine like a arrow with a tail surface here, right? If your arrow is pointing into the page, you're gonna see the X. If your arrow is pointing out, you're gonna see the circle, the cone, right? So just teaching you little tidbits of knowledge there. Right, so this is the center, this is our circular cross section, which is gonna link up, right? We're gonna have a pin here, and it's gonna link up to the bridge, and I'm gonna call it a bridge. I'm gonna write that down, right? And then it's gonna coil around this structure, come back down. So it's like a linkage like that, right? And then here it's going to be connected to the pin that drives it, and this coil wraps around this the piece that actually connects to the horizontal tail. Right, you have your tail surface here, whatever, right? And then it goes there, and then there, something like that. And then this, we just drew out this pattern right here. So we're determining this height and how much to go across. Sorry, you couldn't exactly see that. And then here, at some point, we need to build like an anchor point, like a pivot. And that's usually done with like a brass fastener. Here, I'm not sure if I can fit that on in a conventional way. You might have to wrap this, the two legs of this brass fastener, it's like a, kind of looks like a pi symbol, right? Cross section, if you look from the side, it's kind of like that, right? Round on one side, flat on the other, and then it's got these two tabs that come out like that. This is like straight off the side looking at it. So you might have to, if you have your edge of this material, right? I'm thinking we might have to fold these two, right? The first leg on top and the second leg, we're gonna have to wrap around like that onto the bottom side, and then our, rotation point is gonna be right there. That's the center of the wire. But I'm just thinking, that's like a thought. I don't even know if I'm gonna actually do that. But it is what it is. We need to determine these lengths, height, width. I'm gonna call this length because it's perfectly works. Right, it's not a prism that we're dealing with right here, so we can use these three letters and know exactly what we're meaning here. All right, so height is interesting because you don't want it to be too high because your mechanism has space constraints. You don't want it to be extremely voluminous, right? But you also don't want it to be too close to this, because what enables the movement of the mechanism is if you imagine like the straw like this, and then you have your pin, right, and then it connects to this piece, right? This amount of difference here determines the allowable movement, right? You have an arcing circular movement here. You want to have enough throw to move your control surface down, in this case to pitch up, right? And then up, in this case, to pitch down, which probably not going to use most of the time. But you need to determine how much height to give it. This is the hardest part, I guess. This is like, I don't do precise calculations exactly. I could try and do it. I haven't done the math. Like my undergrad degree was aerospace engineering, so we have literally zero experience designing mechanisms, and here I am designing a mechanism. So we're gonna try this to get a better feel for the numbers. So we have a throw distance of 1 centimeter. That's really nice. Okay, so that's between the neutral point and where we want it. So let me draw another sketch here to the side. Just do some preliminary calcs. Right, you have your slot, you have your neutral position, N, and then you have what do we call it? In this case, we have D, which is down, and pitch up. And our pivot point is after that, so between our neutral point and the hinge line is 1.5 cm. So it's really there if we want it to be accurate, right? It's an eyeball, like half of that is approximately right there. So what's the angle, right? What's the angle that we want? I'm thinking we don't need a lot for this. Maybe at most 15 degrees, even that's a lot, you know. 15 degrees plus 15 degrees here, minus 15 here. So at this hinge location right here, we want, you know, if you imagine like this point, wherever it is, this motion to be plus 15 degrees here, pitch, or, you know, plus 15 degrees, and then minus 15 on this side, right? And you have, you know, you have concentric circles here essentially, and want to determine with 1 centimeter of throw backwards. We don't have to use the full centimeter, right? We also have height constraints based on the actual geometry of the tail, right? So I'm just thinking through this right now. Right, so this is gonna be 1 centimeter this way, 1 cm, and then a throw, right? And then our link here. So in its neutral position, we have a triangle. This is kind of hard. I don't want to do this. It's not as straightforward as you think, because this is not exactly at the center. If we assume that it's a right triangle, then this becomes a lot easier. But in reality, this is underneath this point. So if we assume a right triangle, let's see what happens, right? We have 1 centimeter of throw. Let's see if we use that full centimeter. We don't know our height here. Question mark. And okay, that's not enough information. Okay, so we have 1 centimeter and then 1.5 centimeters. That's okay. So that's where the hinge line is. So that's not right. That's so you have 1.5. That's 1.5 right there, all the way to the front, right to this point. I guess what if that's 15 degrees, then if you move half, you get 15 degrees. How high do you have to be? Okay, let's draw this a little bit bigger. If we assume a right triangle, we have 1 centimeter here, 0.5 centimeters here, we have 15 degrees off, plus 15 degrees here. I need a compass. shoot, I don't have any lead in this. Damn. That sucks. I'm gonna try and see if I can cut that lead out. There we go. It just broke off on me. We don't need a very precise line, we just need to have enough here. Alright. That point. Okay, that's really all we need. We don't need a full circle. So 15 degrees, and just clean up that line right there so you get a good feel. I think from my experience I'm gonna do like half a centimeter just to give enough space, but I am just curious right now to see how much we actually need. How much height? If we give it more height, it'll reduce this angle. When you give it less height, with the same amount of movement, you're gonna have greater amount of throw. Well, so 1 centimeter and 1 centimeter is gonna be approximately 45 degrees. Right, that would be 45. Let's see. It's not really like that. It's like half a centimeter going up. So we have 1 here and then half here. Right. And then half here. Oh wait, no, half here. No. This is the center line. Go half up, half down. This is the anchor point. If we have our arm here, have a connection like that. That's gonna give us plus 15 degrees here. I know this is exaggerated, but for sake of illustration. Well, right, this all kind of lies on one assumption, which is that we use the full amount, which I doubt we're going to need. So if we give it a little extra, but enough so that the mechanism doesn't take too much space, then it should be okay. Let me see here. So the diameter of the straw is not 1 actually, so it's a little under 1. It's about, I want to say, maybe 8 millimeters, 0.8 centimeters. That's the diameter, right? Okay, so if it's that, let's see what looks like a reasonable amount. I don't think I'm gonna do actual calculations for this because I don't want to do it. I just don't. If it was easy, I would do it. If it were easy. So it looks like 1.5 1.2 seems about reasonable. That's like half the diameter here. And then the width, we could just do width, we could do 1, give it enough bending space. We could do 0.8 cm. Okay, so we have our width, which is 0.8 cm. We have our height, which is, this is 8 millimeters. Our height, we're going to use 1.2 cm. That's 12 millimeters. And then this length right here, well, this is 8, and we're aligned right here, so that means 4 here. And actually, we could just measure directly. That's going to be 2.1, so a little over 2. But we need to subtract the diameter, half the diameter. We need to subtract the radius. So 2.1 minus 2.1 minus 0.4. 2.1 minus 2.4. That's going to give us 1.7. So 1.7 here. That's 17 millimeters. All right. So we have some basic dimensions here. This height I just ended up eyeballing based on past experience. I think it's gonna have enough throw. Actually, we have a mechanism in progress, or not a mechanism in progress, an aircraft in progress, which I'm gonna take out again for illustration purposes. This is the YX10 M1 prototype. It's not done yet. It still needs some skin paneling work. But this mechanism right here, we can actually take a reference and can try and measure this. All right, just need to move this camera up a little bit. This is about 1.2. Wow, I didn't even know. I just eyeballed it. This is about 1.2 centimeters at the center of the circle, if you notice that, right? That's actually, wow, I eyeballed it right on the dot. Okay, that's rather convenient. 1.2, so I guess for my standard work, so to speak, this additional height right here has to be half the diameter. So, you know, you have your length here, right, which is you have your diameter of the tube, which is 0.8. So whatever this total height has to be 1.5 times this, which is 1.2, right? Because that's, you know, that's 3/2 times 0.8, which is 2.4/2, which is 1.2. So that makes sense. Yeah, so it's just held together by simple proportion is what I'm getting at. You don't have to go through all of this, you know, kinematic calculations and whatnot. You could. I just don't have the brain to do that right now. And from past experience, I know that 0.4 is a good number. So kind of saw my thought process there. You know, when it's too hard, you just kind of use empirical data and in the past, you know, rely on your experience, because that's not for nothing. And we can use that to determine your length. Okay, so we have an idea of what we want to make. Now we can actually start forming this piece. We're going to need a paper clip for that. And let me just grab one from my drawer. Last time we spent a bunch of time trying to find these elastic bands. As a kid, I had braces. These elastic bands are plentiful to me, but I'm pretty sure you can get these on eBay or something for pretty cheap. You know, you know, couldn't have been done without new pliers, of course, but we did like a question mark shape here just to really tightly grip this. We need this elastic band for pretension in the mechanism. You don't want it to, you know, just flop around in the air, so this is important. That was off on a tangent. I apologize, but just gonna find a paper clip real quick. And all right, got one. So this is gonna be our tail surface thing, I guess. I kind of like vary my terminology on this, but I really should be more consistent on naming. So a linkage, right? So you have a linkage pin, which is what's going to be in this straw, right? The pin moving from neutral point to forward and back, to up and down for pitch up, pitch down. And then, so that's the pin. And then you're going to have a linkage arm, right? That connects this linear piece to a rotational piece, right? This part is going to be turning. And then this piece that's turning is the one that's bothering me. That's like the output, I guess. Really, it's the output, but it's the part that's being moved. So I'm not sure what to call that. Maybe like a, I was gonna call it output, rotational piece. I'll think of a name, and when I do, I'll try and mention it. But in the meantime, we need to unravel this paperclip to really get a feel for how much material we got to work with on each side. Our calculations are on that piece of paper, so we're all good. I don't have to remember anything. So the way I do this, right, you just hold it down really tight, apply pressure down and into the ruler. Try to keep it flat and just kind of unravel it like that, right? There's a little bend there, so you can just slowly work it flat. Okay. Alright, out of plane, it's bent a little bit, so just want to correct for that. Also want to get my tool ready for some heavy duty bending that's coming up. So I'm just grabbing the pliers. Alright, so this is nice. Okay, bend it a little bit more. This is kind of an art. Without a machine to do this, it is kind of up to your eyeball and how sensitive you are to these things. Okay, we're gonna unravel this section here. Let's do the same thing, right? You'll notice this part is bending upwards a little bit. That's why I'm holding it a little bit closer to this point where it's being bent. Okay. Again, if you have like a stock of wire material ready, that's not paperclip, that's a thin diameter, you know, by all means go for it. Use that. It's easier to use that and straighten that than a paperclip. The reason I use paper clips is because it's relatively cheap and plentifully. There's a lot of it. It's very available. So to use things that other people can access to in case you want to replicate, but not many people do replicate these things. So each one of these is, to me, it's really a work of art. Well, it's not exactly art, right? It is functional too. It's somewhere between an engineering project and an art project to me. It's kind of where I've always resided as a person in general, with interests in both STEM and the arts. So it's a little bit of both. The end goal is common: create something beautiful. So this is kind of hard to kind of gauge the straightness here, but I think it's good enough for now. I'm gonna measure the length of this. Let's see, we have approximately a little over 15 and a half. 15 and a half centimeters. Great. If we calculate that, essentially we're allowed 15 and a half over 2 for both sides. So 15.5 over 2 is 7.5 plus 2 point. Nope, that's not right. 7.5 plus 0.25. There we go. Right. Half of 15 is 7.5. Half of 0.5 is 0.25. So that's going to give us a total of 7.75 allowance on each side. Or not inches, cm. I have a habit of switching units. So 7.75 on each side. If we have 0.4, so we're going to start at the center. Right? We have 0.4 coming out. Going down, we have 1.2 plus 1.7 . So just the internal part. This is the part that's inside the fuselage. That's gonna be, let's see, what is that? That's 1.6, 1.6 plus that, 3.2. No, 3.3. Damn it, I can't do math. There we go. Right, so that's 1.6 and 13, and then carry the 1. That's 2, and then that's 3. Okay, cool. So it's 3.3 internal. Oh, sorry guys, that was not on camera at all. Here you go. Here's the calculation, right? So we have 7.75 allowance, right, from dividing this length by 2. Internally, we have 0.4 from the middle here. 0.4 plus 1.2 plus 1.7, which we just did the math here. That gives us 3.3 centimeters internally on each side, which fits within this allowance, thank God. That means 7.75 minus 3.30. That gives us 4.45 cm left, right? And then this is going to be used for this part of the horizontal stabilizer. So we're going to see how far we can get with that. Let me just check something real quick though. This is so 1.7? 1.7? Right, that's 1.7. Okay. Okay, that's good. 1.7 is good. All right, so we have 4 cm external. Right. So let's see how far we can get. So going up to here, that's about 1.6-ish. Let's consider this. If we have 4.45 minus 1.6, that's 5 there, 14, 8,
minus that 3 to 2.85 left. So that's going to get us up until this point right here, which is decent. But that also means we don't have enough. We don't have enough to go back. That's troublesome. All right, so it's not long enough. So if we use this piece completely, and we assume no loss in length due to kind of these fillet radii, because you need length to curve. It's not gonna be a straight right angle. If we assume we use 100%, we're only gonna get about here on each side, which isn't great, but you know, what else are you gonna do, right? Options are really limited here. The only idea I can think of is bending this, so instead of going up here, we can lose some structural rigidity there to go perpendicular to this edge, but then you have like a crease line there, which I don't really like. So I don't know. I feel like we should just go as far as we can, and hope that this aft part here doesn't take any load, right? I mean, if you think about it, it's probably not gonna happen, because on the F-16, we look at the sketch again. The dimensions of the wing are probably enough, right, to protect, you know, so if it turns upside down and crashes, then you have this length, which protects from the vertical tail to the wingtip, which is just going to protect the tail here. And if you do stall and crash tail first, yeah, it's gonna be an issue. It's not gonna be enough. Okay, that's might be a problem, but all right, if our plane flies, then we won't have to worry about this. But I'm a structures guy by training, so I have to think about this. I always think about, in case it breaks, what's gonna happen. That way we have the most reliable plane. But God, we don't have enough. We don't have enough room. Is a triangle enough? Is it sufficient? Right? If we only have this bit right here, is that gonna be enough? I don't know. I am not sure. Yeah, that's an interesting question. I want to say no, but I need to make this. I don't have a longer wire either. I mean, I do have like wire, but it's like really, it's too thick for the tail. It's not gonna work. And plus, I don't want to use like really heavy duty wire. That's too heavy. Stay consistent, right, with paper clips. It just terminate it in a triangle, I guess. We don't have to extend it back. So these two horizontal lines, they're not gonna be, there's not gonna be a wire there, because unfortunately we don't have enough length in a regular paper clip, and we don't have like a stock material that's this diameter and has these material properties. So we're gonna go with triangle, I guess, because I don't want to like make a perpendicular fold here and then go back like that. That would be more rigid, but yeah, that diagonal bit really bothers me, because then the leading edge is weaker, right? Not only does it look bad if it creases, but the leading edge is also going to be weaker, and I would prioritize the leading edge over the trailing edge. That's my design reasoning. Okay, so we're gonna do the triangle because we don't want the leading edge to be weak. We'd rather have the trailing edge be weak, because chances of a straight on tail collision with the ground is probably smaller than collisions here. So I'm gonna do the triangle. All right, cool.
made a decision and we're gonna stick with it. Alright, so with that said, we can start bending the wire. We have all the major dimensions. We just need to mark out proper locations. Key points, right? So is what I call them. So what you're gonna do is, I do this like a tutorial, but it's really not a tutorial, it's just insight as to how I design and make stuff. Alright, so we have 15 and a half, right? We divide by 2, we get 7.75. Right about here. Okay. Seems good. And then we start laying out key points where we want to go. So that's going to be 0.4 this way. Right. Go 0.4 this way, just align it with proper mark here. We'll be at this location right here. And then 4 here. This location right here. Right? And then we're going to go down approximately 1.2 centimeters. So 1.2 centimeters right there. And then, just to make it easier for myself, 1.2 centimeters right here. Looks good so far. 1.7 after that. And again, this is just for reference. We don't have to bend right on these points. .7, and then, oh shit, is that 1.7? Nope, that was 1.2. See, I make mistakes. I'm not perfect. Well, luckily, you can rub this off mostly. Alright, 1.7. 1.7. There we go. Much better. And then 1.7 here. 1.7. Great. And then we can bend the rest after that according to this shape. Yeah, it's like 2 point something, if I remember correctly. 2.85. That's almost 3. We'll see how far we can get, but we have a starting point to start bending the wire. Alright, so let's do that then. Okay, this is probably the most frustrating part about this whole thing, but it's gonna be necessary. Alright, cool, so I'm gonna hold this in place and we're going to fold a 90-degree angle. Looks pretty good to me. Full 90-degree angle here. Right. It's pretty close. A pretty sharp angle. Just a little bit more here.
This needs a little bit more. Okay. Here we go. Right. Just inspecting it, checking. Looks okay. Yeah, this part is not incredibly straight or precise, but I'll have to make do. Okay, so that part's done. We have a dry fit around this, right? That's enough wiggle room here. Right, so the reason why we have this gap, right, this tiny gap, I'm not sure if you guys can see, is the bending radius, right? It bends out. So the horizontal part is indeed that 0.8 length. But when you curve out, it's going to give it a little bit more gap. So just manufacturing know-how, I guess. Okay. We can make the next fold. It can be an internal fold. What I mean by that is grab right on the inside of the marking and then make the marking be on the outside, and then fold that piece. Right, we don't want it to be like that. We want it to be like this. And it's gonna fold out. Ah, shit. Alright, yeah, this is tough. Tough to do. It's not easy. Okay. That looks pretty good. A little bit more angle there. Right. Whatever you do, you want to make it consistent. Right? Even if you make a mistake, you want to be consistent with that mistake. Oh, that's probably like not the thing to say, but sorry, I'm just really focusing in right now on this part. Fix the in-planeness. Shit, they're at slightly different heights. Which one do I want to correct? Yeah, that's a problem. Okay. I think I'm gonna fix this one. Alright. You have a limited amount of tries for this to get the geometry right. Enough for the tail? Yeah, that's about as large as we can get it. This is a interesting bit right here. Need to fix the torsional problem. It's not in line, right? It's not in the same plane, unfortunately. There's a little bit of play, right? Okay. I think we fixed that. Okay, just testing this. See if it wobbles when I turn this. No, it looks fine. Okay, looks good. Okay, now I'm gonna dry fit this, see how it holds up. Neutral point, hinge line, right? This hinge is gonna be right at this edge. I'm gonna have a thing going forward, linkage arm, then where do we mark that point? Okay, for my reference here. That point is right about there. Okay, that's good. Okay, yeah, so I'm gonna extend this point around the wire just to get a better view of it. I'm gonna extend that all around just so we can have a clear view. This is the next bend point. And then this on this side. Okay, a little dry, this marker. Why is this marker dead? That's not nice. It's supposed to work. Anyway. Hey, that's the next bend point. Bend point done, marked. Alright. It's gonna be like this, right? So it's gonna be vertical. And then this tail part, which is, okay, so this wire is gonna be back here, centered, right on the edge. And this is gonna bend forward and then come out. Okay, that's kind of the plan, is to bend this forward and then back. So it's pretty simple. You just follow the line. And we do have the point marked, although this is quite faint because the marker decided to die on me. This is approximately in the middle. Damn, dude. Why you gotta die on me like that? Come on. There we go. Ah, that's a thick mark. Anyway. Have a bend point there located. Just gonna bend it forward. I do have another set of pliers actually. I think it would be better to use those. This one has a proper 90-degree lip, so to speak. Okay, so this part is parallel. This, on the other set of pliers, it's a needle nose, so it slants down, so when you fold it tends to bend in different ways in a different plane. So it's good to have different tools available to to switch between. So I'm going to pinch the inside of the wire, of the point, and then bend it forward for the right side. Right. That's actually a much better bend than what the needle nose. Right. Nice. And then gotta bend it again at a certain point. Just mark it as that corner. I'm gonna hold the inside and bend it again. But before we do that, we're gonna bend the other side. Because like I said before, you don't want to forget what you did. Right, so this we folded on the outside. We held the inside and then folded the outside. We're gonna do the same here. Okay, it's on the outside. Looks pretty perpendicular. And you just fold that 90 degrees. This is great when it's easy. How does this look? Does it look symmetric? Yes, it does. This does need some straightening though. There's some metal work here. Might need to bend a little bit more. To get a right angle, proper. Look at how perfect that is. Look at how perfect this part is. Damn. Handcrafted precision. This doesn't look too entirely straight, but I think for the most part it'll do. Right, we started with a paper clip and now we have this well-defined part. And you only used pliers to help us make some certain bends. I mean, other than that, it's really nice. Yeah, that's great. Okay. Now we're going to proceed forward. Now that it has like this kind of square shape, it can stand on its own, which helps with the build. Just gonna line it here with this line, panel line, or not panel line, you know, the marking on the mat, cutting mat. Hinge line located. Marking set. And then we're gonna hold. I'm gonna hold the inside or outside. Did I say inside? I think I said inside. So I'm gonna do the same measurement on the other side. This is from the end of this part. It is 1.15. All right. What do we have for this measurement? 1 point. I have no idea. 1.7? It's somewhere on the paper, I'm sure, but Oh wait, no, we got to this point and then we said like whatever's left is whatever's left. We can do whatever. Because it's gonna have to use up all of the wire anyway. We're not gonna have to cut for this one. Unlike for the slats. Do you have extra for the slats? So 1.15. Alright. I'm gonna do the same thing on this side. Except this time we're gonna mark out the 1 point. Alright, this is when having a nice working marker is nice, because then you can leave it uncapped. But since our marker is dying a little bit, can't really do that. Alright. God damn it, this is hard. Right about there. Okay, I have a light mark. And then you can just darken it a little bit. Okay. That doesn't look the same. It's not 1.15, it's 1.65. Damn it. Oh, and that's why there's a 1.7 there. God damn it. Alright. Yeah, I read the markings wrong. So it's about 1.65. 1.65. Yep. 1.65. That's gonna bring us up to here. Great. Alright, now we can do a quick sanity check, right? It's always good to have sanity checks. We'll make sure that this is the right length on each side. Looks pretty parallel to me. Right? This and then this, right? Same length, both sides. Great. Now comes the fun part of making a really tight turn. Or tight. Where did my tail surface go? Damn. Oh no, it's hiding underneath. There we go. Alright. This is the fun part because this is probably going to be the hardest part of this entire fold. Alright, we're gonna hold the inside and then fold over. And then it has to be this really sharp fold. So to start, let's get a 90 degree fold, right? Oh shoot, got it. Alright, there we go. And so it's going outwards. Alright, just gonna hold this tight and make sure it's 90 degrees here. And then fold out. Okay, that's good. Alright. Just start with a 90 degree fold. Hold on the inside of the marking. Make sure it's perpendicular. And then rotate it a little bit. Inside the marking, align properly, and then fold. Approximately right? Yeah, that's pretty close. That's not too bad. Okay. Now that we have that. Oh my god, we're at 104 minutes already. I usually go until, what is it, 130? 130 minutes, which is a little over 2 hours, 2 hours and 10 minutes. So I just stop at 2:09. It's 130 minutes, so we got 25 minutes left. All right. Yeah, it's amazing how fast time flies when you work on these things. It's a good way to pass time in quarantine. All right. Okay, looks good. Just visually inspecting all the parts. Okay, now we just need to fold this very, very sharply. And that's gonna be kind of hard. Okay, these needle nose aren't gonna do it. Probably gonna need these. It's hard to do this. But we're just gonna have to power through here. Just grab it, and you need a little bit of room. Then just kind of bend it. Yeah, this is kind of tough. I don't like sharp bends. Maybe I should have thought about that in the design process, in the decision-making process. But I always say that's a future me problem. That's a little excessive, I think. Yeah, it's just a little tiny bit excessive. Right, we can straighten this part. You see, like, there's a little subtle arc right here. You gotta correct that. And then once we correct that, we can make adjustments to the final angle here. Right. Lines up. Yeah, that's about it. And then, just adjust this 90-degree angle here. It's a little bit off. But for the most part, we have one side done. This is all we need. I'm not sure if this is enough secure anchoring, right? We really do need that little bit here to make it stable structurally. I mean, triangles are stable, right? 3 points determine a plane, but it's just it's a little questionable because it's literally a tape joint connecting this wire to this. So we'll have to be really good at securing it when the time comes. Which is maybe in today's session, but also maybe not. So we need to see how far we can get first with this. Can you fold this? So I think I grabbed the outside with a little gap and then tried to fold it in. Right, like that. Okay, that was just a first pass. I'm not expecting it to match up. Alright, let's move this over a little bit. There we go. This is the left side. So we have this bend. Right, it's gonna be good. Needs to be a little more. Okay. Let's see. Does this work? Have that there and that there. Yeah, okay, it's a little off. That's to be expected with manufacturing tolerances, right? For the most part, it matches. Let's fold this in a little more. Tighter 90-degree angle here. Better 90-degree angle. And then loosen up this side a little bit. I mean, as in like widen. There you go. And then this pretty much lines up. Half and half. It's not perfect, but it'll do. Right, there's a tiny gap here in between the wire and the marked line where it's supposed to be. It should be good. All right, that's pretty much it for the tail. We made that part. This is gonna connect both of these tail surfaces together. And so the next step would be to create the linkage arm, wrap this around, have these two hanging off of this bridge. And then once we have the neutral point pin set in place, we can start wrapping around that pin, which will secure that. So I guess we can get started on that. We do have, I think, 18 minutes left, so let's see how far we can get today. This has been pretty nice. Made a lot of progress. I'm just inspecting the part that I've just made. I think there's a little bit of out of plane alignment issues, but those can be fixed with minor adjustments. Overall, it's a solid piece. Okay. This is good. So we have all of the hinge parts made. I just need to create the linkages. Right, to do that, well, the linkage, there is no linkage for the leading edge slats. That's important to note. When you look at this, right, the linkage doesn't exist because we have a rubber band and we have essentially what's going to be a horizontal rod that's like, it's like this, and it's going to be pushing this forward, which will deploy the slats, and then the elastic will bring it back into neutral. So there's no linkage for the leading edge slats, but for the tail, for the horizontal tail, it does exist. You do need it to have a proper actuation method, I guess. And to do that, I'm going to use another paper clip. Just gotta find that box. Yep, right here. Just grab a spare paper clip.
white and blue. I'm gonna use white because it's easier to see. On the astral one, I use blue. Maybe I should use blue. I'll use blue. White, I don't know. It really doesn't matter. It's just a matter of personal preference, but I like to be consistent with what I've done in the past, which is, I guess, in the M1 I use blue, so I'm gonna use blue here. It's the same story. We're gonna do the same thing for preparation. We're gonna unwind. Oh, this is gonna be hard to see. That's why white might have been a better option here. But this blue, we're going to unravel it, same as before. To straighten the paper clip. It's the first operation. Right, like that. There we go. There we go. There we go. There we go. Looks decently straight. Right. Then I'm going to the same thing here. This last curly bit. Alright, doesn't have to be perfect. This is a short linkage. I mean, all linkages are short, at least when I design them. This is probably pretty tricky for some people. It's gonna be kind of hard to really grasp, but you essentially want to wrap this wire around this wire at this horizontal location. The way to do that is, since you don't know how much you need, we're gonna start in the middle. So I'm assuming this is gonna be pretty close to that 15.5 that we got. Yeah, it's pretty close. So we're gonna do 7.75, which is right about, shit, I lost it. All right, I need to mark this again. The 7.75. All right, we have this. There we go. Alright, yeah, I just really should have used white, but for sake of consistency, god damn it. Alright, just gonna take a sip real quick. I have the midpoint marked. Since it's gonna be a tight coil, we're okay with, making an initial loose kind of bend here. Not a tight bend. I mean, the material has its limits too. You can't like bend it too sharply. It's just not possible. So you kind of just wrap it around like that. Right. Make sure you have plenty of excess. We have a ton right here, and I'm just gonna start wrapping it around. It's gonna be kind of hard, but you want to cross it over and make sure they're pinched together. Right? You want to go that way for this one, and then this way for this one. It's just to make sure that it's tight. So I think we have approximately 10 minutes left. So this is probably gonna be the last step today that we're gonna do before calling it quits. But yeah, this is the hard part.
Right? That's good. Just need to pinch it back together a little bit. There we go. Really, the first several are gonna be hard to do here, but you know, it's once you get started, it's relatively simple. It just takes a lot of manual dexterity to constrain it correctly and proceed with the fold. Right, just kind of cross it like that. Right, and do the same thing again. All right, as you'll notice, it's gonna start getting a little bit tight. And that's to be expected, and you do want it to be tight because that's what gives the mechanism a really precise feeling. You do want to correct minor things like how the helix wraps around, right? You want to make sure it compresses tightly against the next coil. And you just keep on doing this until you take up the whole width here. So it probably needs 1 or 2 more turns on each side right here, right now. This is essentially what we're doing here, is making a rotational bearing. This helix, this coil, wraps around tightly against this actuation piece, and we're able to use that, just kind of the material properties to get a nice, precise rotational movement in the mechanism. All right, sorry for the shaky hands. This is just a really finicky part to make. It's really kind of hard to make. There we go. Don't worry about damaging the orange. Just get the coil on, as long as you don't damage the orange too much. Alright, just pinch it together a little bit more. Right. You can also use pliers. That might have been easier, to be honest, to use wires or to use pliers, but you really need to have like a first coil in order to use that. Use the pliers. And then, you know, you see this little tiny gap here, you want to just fix that by pinching that together. Ow. Yeah, you want to be careful with your hands here. And then this side, I think, is almost done. Just need to hold it in place and do one more coil here. All right, and our linkage arm is going to be in front, so I'm not sure if we have enough space for another turn here. I'm going to try and go for it. Slide this over a little bit, right? And then this can be done relatively easily on this side. It's gonna pass through here. All right, that's a nice part. Just gotta fix some of the minor things here.
Okay. All right, it looks good. And now we just need to make the final adjustments here. Got 5 minutes left. What I like to do is one of them is going to be straight coming off, right? I like to keep that one straight. The other one is going to come out on bottom, which is going to be a little tough to align, but you can do it easily with a pair of pliers like that, and then, you know, grip a little bit underneath here, and then bend that, right? There we go. So now we have two pieces that are kind of just hanging off, Jay chillin' on this piece, right? So we just wrapped one around the other. And then that's gonna, you know, the blue part is gonna move forward and back, and that's gonna turn our stabilizer in the back, right? So if you know, hold this in place with a fulcrum, it's gonna rotate, right, when you move back and forth. And that pretty much concludes probably today's session. I'm not gonna be able to do much in 3 minutes. And I like to keep a consistent time here. But this is the key here. One of the key technologies, I guess, in this design is wrapping this, you know, paperclip around another paperclip to get a rotational, very stable rotational movement. So we made this back part here, right? Our tail looks about right. And then next time we just have to connect this up to the main shaft right here at the neutral point. So we're gonna put two of these thin diameter straws through, right? The black straws that you saw earlier that are like this. I'm gonna put two of these inside this, try and get the full length inside with enough for the knob in the back. Puncture a neutral point pin through, which I'm probably gonna use like a silver paper clip just because that's kind of what I used before. And once I do that, once I put the pin through, then we can wrap this blue around that pin and then be done with it. So we have, you know, you define this length to the middle, right? You have enough for the curl, and then you just make it wrap around the pin. And then once that's done, this will be one assembly, right? This will be one tail mechanism assembly. We can constrain this later. We don't have to do it immediately, but having this at neutral point, having the center piece in place is going to help us integrate this leading edge slat mechanism, which we will probably work on next time as well. So yeah, that's pretty much it. Thanks for watching, and I'll catch you guys, I guess, in the next stream, which will be next Friday instead of Thursday. So yeah, if you have any questions, leave it down in the comments. Otherwise, you know, stay safe, and yeah, I'll talk to you guys soon. All right, thanks everybody.